Hello, everybody. Welcome to the downstream processing in biotechnology class again. For this lecture, we will continue on the adsorption. Previously, we talked about the three kinds of adsorption isotherm, right? Langmuir isotherm, Friedrich isotherm, and linear isotherm, and also give you some example. For today, I will talk about the ion exchange, affinity exchange for isotherm. That's why for the ion exchange isotherm. That's why the ion exchange isotherm means the adsorbent surface have some ion. That's right. If the cation exchange, that means adsorbent surface should be an ion. For anion exchange, adsorbent isotherm, adsorbent surface should be cation ion, something like this. For this case, show you right some reaction like we have like sodium ion. Sr is the adsorbent layer, and then after interchange between Sr and sodium ion. That's right. For this case, resin represent like Sr and Na represent the ion exchange site. That's right. The exchange between Na and R. That's right. Na will adsorb on the resin, and the hydrogen will remove out from the resin. For this example, that's right. And then you can calculate like the equilibrium constant. K is the concentration of NaR. Hydrogen divided by sodium ion and NSR. That means we can calculate the total concentration of inorganic group on the resin, which is fixed, is constant, is equal to concentration of sodium that adsorbed on the surface of resin and hydrogen on the resin. This is the total. And that we can calculate the concentration of NaR in this term. Mostly in a buffer solution where hydrogen ion is constant, we see that the sodium adsorption is less and will be the Langmuir isotherm. This is approach to the Langmuir isotherm. For the second example, calcium ion. For this case, different is two parts. This is only one. It's different equation. This is the calcium ion exchange with the resin with sodium ion. And then calcium will exchange with sodium. Calcium is 2 and 2 sodium. Again, we are consuming the side will fill with either sodium or calcium ion. And then you can calculate the equilibrium constant like this equation. And then we also calculate like is also constant the total number of sides. This is NaR plus 2 CaR2. And then for this case, we can approximate like the isotherm for this example is Friedrich isotherm. For the Friedrich isotherm, this is the example of ion exchange isotherm. Please note that the ion exchange adsorption means that the surface of adsorbent is contact. The surface is modified with the cation or an ion. Cation and ion, we interchange between the ion. And for the next adsorption, we call affinity adsorption. Affinity adsorption is depend on the specific chemical interaction between solute and resin. It depends on the interaction between the solute and the surface of the solid. Rather than the van der Waals force or ionic bond, like the physical bonding, or chemical bonding or physical interaction. That's right. For this case, the adsorption or adsorbent will consist of two parts, support part and ligand part. Ligand part is the specific to some solute only. The support is support for ligand. The support is bound to ligand by covalent or ionic bond. But the support does not react with solute. Only the ligand will react or selectively with the solute. For example, right, for this show you right the interaction of we have like this. Interact with this. This is ligand. Okay, the first step we bind the ligand to the support. It is our support. We bind the ligand to support. We get ligand and support. this ligand is specific to the solute. And then with its solute, is specific solute to contact with the ligand. We get impurity is not contact, for example. This is the adsorption by affinity. And then you can dissolve, you can dissolve the solute and ligand can be degenerate and reuse again. This is the physical, the picture show you how to interact of the affinity adsorption. Affinity adsorption. Okay, the affinity adsorption is include the following ligand most induced bioprocessing like substrate analogous by enzyme, antigen for absorbing antibody. Antigen is the ligand attached in the support or a specific base sequence for binding for adsorb the nucleic acid. And also protein attached to the solid support with capture particular hormone. We use the protein to separate hormone, for example. Mostly the affinity adsorption often show Langmuir isotherm. Most of this. And also we have to check by the experimental data. Okay, this is show you a various kind of adsorption equipment. Is maybe the first one is solid tank solid operation. Solid tank means we have the liquid solute gas mixed together with the solid adsorbent. We mix together, and then after adsorption, okay, we filtrate, separate between solid and liquid, and then you elution or desorption for the further step. Okay, and the next example is the fixed bed. That's right, fixed bed. It is the feed to the base of adsorbent fixed in the column. That's right, in the column. So you is adsorbed in the solid surface or in the surface inside the pore, something like this. And after light product or raffinate is removed out. That's right. And also for the next step, the dissolvent step, we use some solute, we use some solvent to flow across the package to remove some product, on this heavy product or dissolve it. That's right. Or continuous counter current feeds like this, and also we regenerate adsorbent feed, right? Solution adsorbent flow counter current, contact counter current like this. It's a moving bed. Moving bed means solid and liquid flow. Right. For fixed bed, solid is fixed, only liquid or gas flow like this. Okay, this is for example of adsorption unit, adsorption equipment. Right. And also for this, the moving bed, the feed flow in this direction out of some unadsorbed solute move out, and solute adsorbed on the surface, and then we flow the adsorbent counter current, and then absorb the counter current flow, and this adsorbent is saturated to regenerate by some solvent for counter current also. That's right. This some dissolved. This is unadsorbed. Okay, for the first one, we will consider bad adsorption. Bad adsorption, that means we know only the initial step and final step. Bad adsorption depends on two bases, equilibrium and mass balance. The equilibrium constant or equilibrium isotherm, that's why we Langmuir Friedrich linear. For this case, if we assume Friedrich isotherm like this, okay. C and CF, C is the concentration at the initial step or in the phase step. Concentration of solute in solution. CF, concentration of solute in solution. That's right. After adsorption. Q and QF. Q is the final concentration of solute on the surface of solvent. QF is the final concentration. F is amount of feed. P amount of adsorbent. F in the initially and final is the same. P initially and final is the same. We assume constant. That's like P and F. And then if you draw the stoichiometric, the schematic line FCF in the initially. PQF in initially. Sometimes for this we can become like is the initial step, and final step. For the batch process. Both in batch process we call like is the initial step and final step. The initial step with FCF. Okay, no generation, no consumption, no accumulation. Because it's the general mass balance, initial and final, no reaction. Okay, in step equal to final step, or sometimes you can input equal to output. That's that. How about the initial? Initially we feed with F multiplied by CF, Q multiplied by QF. The final step, PQ, FC. We assume F is constant to the process, P is constant to the process. That's right. Okay. And then you rearrange the equation like this. You get Q equal to QF plus F over P CF plus C. We call this operating line. This look like the traction process. That's right. Here we know like the equilibrium line. Q is a function of C, like this equation. Equilibrium line. And also you get operating line. For this case, the easy way you can cross between Q and C. That's right. This is the operating line. This is the equilibrium line. As I for the attack is one step process. The intercept between these two lines is the Q and C. Final concentration of solute as after adsorption. This remain solute unadsorbed in solution. Q is the concentration of solute that's adsorbed on the surface and absorbed. For this case, you can plot between the operating line and equilibrium line, the intercept between these two lines give you some result, the final concentration after adsorption. Okay. For example, right, for this case, gentamicin adsorption. From the first example, we have found that the gentamicin adsorption is follow the Langmuir, follow the ferric isotherm, like this equation. From the first example, Q is milligram per cubic centimeter of carbon, C is milligram per liter of solution. For this problem, we plan to add 10 cubic centimeter of previous unused carbon to 3 liters of fermentation beer containing 44 milligram per liter of antibiotic. Okay, the question is, what percent recovery can be expected? What percent recovery can be expected? Okay, for this case, you can draw right the operating line. The operating line Q equal to QF plus F over P CF minus C. For this case, there is no concentration, no solute adsorbed on the surface in the initial state, 0. That's right. F equal to 3, P equal to 10. That's right. F over P and CF minus C. And then you know, right, the Q is a function of C. Q is amount of absorbed, concentration of adsorbed on the surface of adsorbent. Q is the remain concentration of solute. Okay, and then you plot between Q based on operating line and Q based on linear. You plot this term, Q versus C. Okay. This is for equilibrium line. This is for operating line. And then you get the intercept between these two lines. Q equal to 13.8 milligram per cubic centimeter, and C equal to 0.105 milligram per liter. This is the concentration after adsorption. Q amount of adsorbed rate of solute adsorbed on the surface of adsorbent, and C is remain solute that unadsorbed. Okay, but the question is, what is the percent recovery? What is the percent recovery? Okay, amount of fermentation will contain antibiotic is 46 milligram per liter. This is the amount of antibiotic at the initial stage. It's CF. Initially, we have 46, but finally we have 0.105. 0.105 is amount of solute that remain in the solution. 46 is the amount of solute at the initially in the solution. 46 multiplied minus 0.105 divided by 46 is the fraction. That's right. Fraction and recover. Okay. Get 99.8% recovery. That's right. 99.8% recovery. For this case, we can separate it about 99%. 99.8% is equal to 100%. The side of antibiotic is adsorbed. That's right. Most of antibiotic transfer to the surface of the adsorbent. For this case, 99.8%. In the second example, kinase, that's right, phosphoglycerate kinase. This enzyme is isolated from yeast, can be absorbed on the cellulose. We use cellulose to absorb this. That's right. The absorption forward Langmuir isotherm. The maximum uptake is 70 milligram per cubic centimeter adsorbent. It is Q0. Half of this maximum occur with the solution contain 50 milligram per liter of enzyme. For this mean, that's right, half of this, half of Q0, that's right, contain 50 milligram per liter. That means C equal to K. This is K value. That's right, this is K value. Okay, we have 1.5 liter of feed containing 220 milligram per liter of enzyme. And question is how much cellulose should we add to get 90% recovery of the solute. Okay, in conclusion, for this form, we use cellulose to adsorb kinase. That's right, to adsorb kinase. We know the Q0, we know Ka. That's right, we feed 1.5 liter. The feed contain 220 milligram of kinase per liter of solution, per liter of enzyme, sorry, per liter of enzyme. Okay. Sorry, the feed is contain 1.5 liter of the feed contain 220 milligram liter. That's right, of enzyme. Okay, this is the feed solution. Okay, for this case from isotherm Q equal to Q0 C divided by Ka plus C. We know Q0, we know Ka. Substitute Q0 and Ka. We get the function Q as a function of C, like this. Okay, for 90% recovery, that means C equal to 0.1 CF, 10% of CF. 0.1 multiplied by 220 milligram per liter, this is CF. You get 22 milligram per liter. This is the final concentration of unadsorbed of solute. You substitute C into this equation. You can calculate Q is 21.4. This is C, is Q. That's right. You follow like the mass balance. You follow mass balance. This equation. That's right. This equation. For this equation, QF is 0. There is no solute on the surface of adsorbent at the initial stage. That's right. That's right. FCF 1.5 liter divided by 220 milligram per liter equal to FC. That's right. 1.5 22 plus PQ. That's right. And then you solve for P. P is amount of cellulose that we use to adsorption. We use for adsorption. It's about 14 cubic centimeter of cellulose. We need 14 cubic centimeter of cellulose for this adsorption. Okay, we talk this for the next lecture. I will stop with the next lecture and we will continue the continuous tank for the next. Thank you.